इसकी ज़रूरत है क्या? मेरी आवाज़ मेरे ख्याल से इतनी होगी। अच्छा, वो रिकॉर्डिंग के लिए? अच्छा, ये मुझे इको लग रहा है ना, इसलिए। Anyway, thank you very much for inviting me for this talk. First of all, I would like to thank all the organizers for organizing this faculty development program, Research, Innovation and Novel Concept for Sustainable Development. Dr. Rais Tripathi is one of the coordinator for this, and I just want to tell the relation between me and Dr. Rais Tripathi is that we were in the IIT at the same time while we are doing the Ph.D. over there, and after 2007, even though I am residing in Delhi, he is there and very near, distance is not more than 50 kilometers, but we met today after almost 9 years. So thank you very much for calling me. Ishmati madam, she is there?
Yes.
Okay. Okay. So for inviting me, for giving me this chance to interact with you. And this talk is basically CO2 mitigation potential through clean energy for cement production. So as we know, cement industry is very energy intensive, right? And like many industries are there, the chemical, petrochemical, and so similar. And in fact, this work is I have taken this work from one of my scholar. He is your colleague only. He is working with me for his Ph.D. So he did very excellent work, and at the end itself, I would like to disclose his name and whose work I am presenting over here, and so all credit goes to him only because he did all this hard work. This will be the flow of my presentation: the introduction, energy consumption, source of CO2, and for clean energy, actually we have tried to implement the solar energy in cement industry. Okay, so in cement industry, the energy consumption is basically from either the electrical energy or thermal energy. So that itself, so thermal part only we want to replace with the solar energy itself, and then see how much CO2 mitigation potential is there by implementing solar energy, and some case studies. So let us start with this Viksit Bharat. This is the vision of our Honorable Prime Minister Modi, right? So we want to become developed country, okay, in 2047. For that, in fact, we need huge infrastructure, right? So let me read this. The Viksit Bharat is that the prosperous Bharat in harmony with the nature and the modern infrastructure and providing opportunity for all the citizens and all religions by their own. And for achieving this goal in the 2047, and why did we decide, or the government of India has decided that 2047, because by that time we are going to complete our 100th year of the independence, right? So, our Honorable Prime Minister have the vision to become the developed country, and of course for that we need the huge infrastructure, right? So, infrastructure is directly related to cement, right? So, in the coming days, definitely the cement demand is going to increase very high, and India is the second largest producer of cement in the globally, fine. And of course, the first one is, as we know, this country is China only, right? So more than the 60% of the global production comes from China only. So around 4,400 million tons is a production, and out of that, around 2,500 million tons comes from China, right? And 340 is from this. And this comprehensive plan by the government of India aiming to transform India into a developed country by 2040, the rapid urbanization, and of course, government of India has decided to develop the smart cities, right? So rapid urbanization of modern society has promoted the global concern over the energy consumption, and despite of impending the construction, yes. So still by 2030, actually in the built environment itself, the 70% of the construction to be done, and that will be by 2030 itself. So that you can imagine the how much cement demand is going to be increased, right? And cement demand means directly the energy consumption, because electrical energy we need, the thermal energy we need, somewhere we have to provide the thermal energy itself. Right now the main source is coal only, fine. So that is still, this study is basically related to the how much coal, or if suppose for 100%, 50%, 70%, 90% of the replacement of the coal with the solar energy itself, right? So that calculation, with that all we have done, and yes, this, see that by 2030 the total built area of the commercial building is to expected at 1.9 million square meter, and this is the threefold increase by whatever the figure we have, the 2015, right? So this is all the background basically for doing all this research. Okay, and now that all I have already covered. This cement, one of the versatile construction material in the world for infrastructure development. World cement production is 4,400 million tons during 2021. The producer 170 countries. Okay, and India is significant in the decline with China because of some reason. Okay, and the production of the good increase in 2016, and after 17, 18, 19 because of COVID itself, the production impact over there. 2010 to 16 accelerated 800. These are all the data actually. So now this figure is clear, right? So in just you can see this is the cement production versus year. So it is continuously increasing, and in 2010 it was 3,310, and it is in 2021 it was 4,400. So just you see the difference, how the production is increased. That production is increased means the demand is increasing. This is world cement production, right? These are all data taken from the Government of India website. It's government website only, the statistica.com website. So all the authentic document. So like this, the world cement is currently produced by China, which accounts this much, more than 60%, and India is second largest producer, then the Vietnam itself. The cement is highly unequal with the top 10 country accounting this. I will show you in the next figure itself this thing, and this cement production of India was 2.95 million tons in 1950 to 51, and it increased the 300. Just see at the time of independence, almost it is time at the independence 2.5 million, and it has increased 330 million tons in 2021. So see, this is China production. Okay, cement production from the China. You cannot compete. No one can compete, I think. And over there, this is Japan, Saudi Arabia, Russia, Iran, Brazil, Indonesia, Turkey, USA, Vietnam. We are here, right? So we are second, and that I have already covered. So this in 2011, the world cement consumption was this much, 3.59 billion tons, and increased this much. Okay, fine. So I mean to say, means the energy cement demand keeps on increasing day by day because of the infrastructure development of the developing. And now just see that this is top cement consumer, and consumer of course from the China itself, right? So again, this is a matter of from developing to developed stage. Okay, we are moving from, so definitely we need huge quantity of the cement. Okay, China, India, United States, and see that this is energy consumption. That all related to demand itself. Okay, and this the output of cement increased around 12.1% from September 21 to 22. The prime factor for growing the infrastructure development and government significant initiative for the smart cities. And by 2027, the demand of the cement is expected to 419 metric tons, and to satisfy the huge quantity of fossil fuel is needed. And we want to avoid this utilization of the fossil fuel basically, right? So therefore it is necessary to choose some other source like solar energy for fulfilling solar energy, and other kinds of renewable energy could be there. There could be the biomass itself, okay, biomass briquetting, and so implementing solar energy in the cement industry, fuel as well as the reduce the CO2 emission. So now just see, this is the whole process basically. This is the querying. The querying is a process where we means a limestone mining is basically, okay. So we excavate this limestone from there and transport to the crushing, and this crushing is taking place around in between the 40 to 90 mm size of this particle size we generally keep over there in the crushing. And the T stands for thermal energy. In the querying, thermal energy is required because blasting is there. Okay, this dynamite we generally use for blasting. So we consider that the thermal energy, and transportation, the thermal energy over there, and the electrical energy, utilization of electrical and thermal energy is there. The crushing, again the crushers, heavy crushers are there. That needs the electrical energy. Then the grinding, for the fine particles, and blending and homogenization. So over there blending is needed because these are some other ingredients are needed to add over there, right? Then the preheating is preheating. These are the different cyclones basically, right? And with this cyclone having the lesser temperature around the 300, and 3, 4, 5 cyclones are over there. Fine, and the last one is around 650 or 700 degree centigrade temperature is what is the last. Okay, then the clinkerization process is there. Over there the thermal energy and electrical energy is needed. Then finally the clinker cooling is there, right? No, sorry, the clinker coolers over there. And in fact for cooling, so we are basically, what we are doing, we are extracting heat from there, and that heat is being used to in this process, the preheating, right? So over there, the clinkers are generally be kept at the temperature is around the 90 degrees centigrade. Okay, from here the clinkerization, from here is the temperature is around the 1400 degrees centigrade, and we cool down to 1400 to 90 degrees centigrade, and whatever the heat is released from this process, it will be supplied to this preheating process, right? So then the final grinding and this the packaging and other final grinding is taking place over there, and over there we generally mix the gypsum. We are mixing the gypsum, and that depends on the type of the cement we want to produce, right? So Portland cement is there, and pozzolana is there. Pozzolana is basically when we are mixing what is called fly ash, right? So so different kind of cements that depends on the mixing of the other elements over there, right? And this is the whole process in the cement industry. So of course a lot of thermal energy is required in the different process, especially this preheating and clinkerization. So preheating, over there the temperature around the 700 to 900 we have to maintain over there, and over there the 1400 to around the 1400 degrees centigrade, right? So these are these two processes are very energy intensive, and there itself we want to replace this fossil fuel by the solar thermal. And solar thermal means what are the possibility of solar thermal? The concentrator only, CSP systems. Okay, so this now the technology is the key factor deciding the value of energy, specific energy consumption. So our basically the heat conservation opportunity also we have to see over there. So we want to reduce the specific energy consumption. By this is possible only by reducing the losses only, right? So of course there are a lot of losses, especially heat losses are there. Okay, so that exercise we have done in this study, the 45% losses, 50% losses, some factor, three study we have considered basically. So actually the dry process of the cement manufacture uses more electrical energy than the wet process, while the wet process uses more thermal energy. So now these days, most of the plants are following the dry process only. Okay, so dry process utilizes 75% thermal energy and 25% electrical energy in the cement plant. The major percentage of thermal energy generated from the combustion of fossil fuel. So this, if combustion of fossil fuel is there, then definitely the problem arises of this carbon emission, right? So and the cement industry utilize 90% of the total consumed natural gas clinker production is a large rotary in the kiln, and the Indian cement industry coal fulfill 94% of the thermal energy demand. So this, you can see over there, 94% of the thermal energy demand is fulfilled by the coal only. So while the remaining demand is fulfilled by the oil and other high-speed oil. I think, is it visible to you? Okay, almost. Okay. Anyway, so just it is basically the energy utilizing the different processes, whatever we have discussed in that block diagram. Okay, so the electrical and thermal energy is being used over there. So basically this the clean fuel. So it accounts for 86% over there, right? And the finishing of the grinding, the 5% only, the clean electricity, the 4%, the others only 1%, and the raw material preparation is 4%. So major energy consumption is in this clean process, clean only, right? And over there, so different kinds of fuels, coal, petroleum, electricity, sponge, coke, natural gas, gasoline, and tire also. So this automobile tires are there, no? Those tires are generally used, but now government has stopped that practice to utilize for burning this tire. Okay, so tire was also used. So over there you see the 13% electricity, and coal is 53% of the coal share is over there for the energy supply. Okay, tire less than 1%, natural gas 2%, sponge 8%, electricity is 13%, and the petroleum in the coke is 21%. So like this way, this is the breakage of fuel utilization in cement industry. Okay. So this is electrical energy share in the cement industry. So clean, the 29%, the recleaner is 24%, and measure this grinding and the transport. This is the because conveyors are basically operated with the help of the electricity only. The coal mills are there, and the conveyor, and these are all the different basically the systems which are utilizing electrical energy in this manner, right? So and these are basically the cyclone preheaters, right? And this thermal energy utilization per ton of the clinker production. So this is a wet kiln, long dry kiln, long dry kiln. So these are the different cyclones that you might have seen over there at this side in this figure. So different cyclones are there, right? So there the fuel utilization, this is a gigajoule per tons of the clinker. It is like this, right? And over there the energy utilization for each section of the cement manufacturing industry. This is the mining and crushing over there. Okay, the cement mill, different kinds of milling machines are there. Kilns, the raw this homogenization is there. Raw material grinding is there. The minings, material handling, and other processes. The energy utilized for these are all sections. So this is a breakup of in process wise or section wise. Okay. And just see over there that this is a specific thermal energy utilization in terms of the gigajoule per tons in the clinker, right? And this specific electrical energy use in the different country. And just to see over there, India's specific thermal energy utilization is 3 gigajoule per ton in the clinker. Okay, and there the specific electrical energy utilization in the per ton clinker, this is 88. So this is among all, it is least, and over there itself it is among all, this is least, right? So in that sense, we can say we are producing less carbon as compared to other country, other cement producing country. But still we want to, government mandate is there, still we want to reduce some more carbon emission in cement industry, right? By implementing the renewable energy sources or by energy conservation practices. Fine. So this is a हाँ जी
ज़्यादा प्रोडक्शन भी तो कर रहे हैं, इस कार्बन डाइऑक्साइड निकाल रहे हैं, लेकिन फिर भी ज़्यादा प्रोडक्शन
नहीं, ये पर टन है ना, आप ये पर टन हमको न्यूट्रलाइज कर दिया, पर टन की बात कर रहे हैं।
और सर एक आपने बताया था कि जो जिप्सम आप
हाँ,
बता रहे थे,
हाँ,
ऐड करते हैं,
जिसम ऐड करते हैं 5%, 5%।
लेकिन जिप्सम तो हम लोग जमीन में भी डालते हैं उसके लिए पैदावार बढ़ाने के, प्रोडक्शन के लिए।
हाँ, जिप्सम तो वही मिनरल्स है एक्चुअली। पोर्टलैंड सीमेंट जो है, जो ओपीसी और पोर्टलैंड सीमेंट जो है, उसमें 95% आपका ये होता है, क्या कहते हैं ये CO है, कैल्शियम ऑक्साइड, राइट, कैल्शियम कार्बोनेट जो है वो से अभी मैं बताऊंगा आपको, ठीक है। और 95% आपका जिप्सम होता है पोर्टलैंड। फिर अगर 30-40 एक्चुअली सीमेंट का अगर आप देखेंगे तो सीमेंट बहुत वेराइटी की होती है। आपने देखा होगा कि सी में जो है, सी में जो पिलर्स लगे हुए हैं, सी में जो सीमेंट और कंक्रीट का वर्क है ना, वो सीमेंट एक अलग है और आपकी नॉर्मल सीमेंट है वो अलग है। और कुछ सीमेंट ऐसी होती है वो टाइम के साथ साथ वो स्ट्रेंथन होती है, कुछ सीमेंट ऐसी होती है, वो सिविल इंजीनियर्स है ना यहाँ तो, आई हैव वेरी लेस नॉलेज है ना, ज़्यादा मुझसे मत पूछना हो उसके बारे में क्योंकि मुझे बहुत ज़्यादा पता नहीं है, लेकिन हाँ इतना ही मुझे मालूम है, देयर आर मेनी टाइप्स ऑफ सीमेंट्स एंड दैट ऑल डिपेंड्स ऑन द इंग्रेडिएंट, राइट। और कुछ सीमेंट होती है वो विदिन 48 आवर्स वो अपनी स्ट्रेंथ फुलफिल कर लेती है। कुछ सीमेंट ऐसी होती है ओवर ए पीरियड ऑफ द टाइम, आपने देखा हो किले हैं बहुत पुराने वाले किले जो एंशियंट टाइम के बने हुए हैं, मतलब बहुत पुराने 200 साल 500 साल पुराने किले हैं, वो उनका कंसेप्ट ही है कि वो बनने के बाद वो दे गेट मोर, देयर स्ट्रेंथ इज गेटिंग मोर एंड मोर, है ना, टाइम के साथ, है ना। तो इसी ये है ये कंसेप्ट, तो ये सीमेंट भी का भी यही है। अब अगर हम सही तरीके से अगर सिविल इंजीनियर्स प्रैक्टिस करें तो कंप्रेसिव स्ट्रेंथ के अकॉर्डिंगली हमें सीमेंट को यूज करनी होगी अगर सही तरीके। अब क्या है कि अब जो मिल गई वो हमने लगा दी जहाँ पे भी है, राइट। अगर हमें कॉलम यूज करने हैं तो कॉलम के लिए अलग होना चाहिए, तो है तो सारी चीज़ें, लेकिन हम कितनी प्रैक्टिस करते हैं वो डिफरेंट चीज़ है, राइट। तो ये स्पेसिफिक एनर्जी, थर्मल एनर्जी यूटिलाइजेशन, मैं ये यहाँ पे यही बताना चाह रहा था कि जस्ट आई वांट टू हाईलाइट इट ओवर देयर, we are means consuming less thermal energy and as well as electrical energy per tons of producing the per tons of cement, right? Now actually over there are only two sources of emissions, two sources of CO2 emissions in cement industry, है ना. So one is the calcination of the cement raw material at a 900 degree centigrade, right? Of this cancellation, so whatever this is, okay, this we cannot avoid. CaCO2, CaCO2 3, it is breaking into the CO and CO2. This we cannot avoid. ये हम अवॉइड नहीं कर सकते, क्योंकि ये तो भाई हमको तो कैल्शियम कार्बोनेट हमको यूज करना ही है ना, और कैल्शियम कार्बोनेट अल्टीमेटली हमको ये ब्रेक करता है, हमको यही चाहिए, है ना. तो CO2 has the two different sources, the combustion of the CO2 and this combustion of the fuel that we can control, and the chemical reaction of the salt and oxide, the CO2 and cement manufacturing process, there are two this calcination process. This we cannot avoid. ठीक है ना. So we can work out only the combustion of fuel itself. We can replace the fuel, or otherwise or the combustion of the fuel that we can also in the controlled conditions, the complete combustion for the fuel could be there, right? So and about half of the emission during the cement production arise from this reaction. So almost the 50%. So कुल मिला के ये है कि हम we can control only the 50% of the CO2 emission, whatever is producing by the cement industry, right? So sintering to produce the clinker is 1350 to 1500 or around 1400, right? So this is one of the process. This is operating module where solar calcination process raw material through the storage silo that we can implement over there. So heating up a gas stream and a hybrid operation, the fraction of the raw meal calcination is carried out, the additional calcination while the completing complement is calcination is existing calcinator. So this is again this is a preheater, and over there itself in this portion we can implement this solar calcination, right? So preheating of this, all these are the same that we have discussed over there. And this could be the scheme. This is one of the scheme. One more scheme is there. So these are the helistate, right? These are the helistate, and over there the reactor, we keep the reactor over there. So sun radiations are coming and reflecting towards and pointing on this reactor itself, and over there we can have the storage material, the salt hydrate over there, and otherwise again whatever the energy we are getting during the daytime, during the sun, without energy storage systems that we can utilize during the sunshine hour, right? And or otherwise another provision we can have we could have the salt hydrate for the thermal energy storage, so that stored energy we can use during off sunshine hour or during when the sunshine are not appropriate. So this is the top of the tower concept, and the same thing this reactor we can keep on the plate on the bottom itself. So this could be now this helistate, then the rotary kiln, this okay, hot gas is supplied in rotary kiln, then the thermal storage, and this is again the excess of the thermal energy we can store over here, right? So this is another way for implementing this helistate fields over there. This is the reflector, and radiate this reactor we keep reactor on this the ground level. So the benefit over this scheme to this this way okay is that only maintenance is easy, right? And this and of course this construction of this tower, and it seems very simple, but it is not like that. It is very complicated process. The outgoing inlet, outgoing incoming and outgoing hot gases are there, and supply and many things are there, right? So reactor definitely if something is operating reactor is very high temperature in the around 1000 degrees centigrade or 900 degrees centigrade, definitely it has some many problems, corrosion and many problems, and frequently the maintenance problems are there. So in this way, but at the same time the cost of the system is increases, and this reflector get deteriorate very frequently. So this is another problem. So cost is in this system much more as compared to that thing. Okay? So this process is same basically. The over there basically raw material starts from there itself. Feeding raw material feed at the preheater, the pre-calciner, rotary kiln, then the clinker product. Fine. So what we are doing over here, this is the helistate, and radiation coming and reflecting over the solar reactor, and from there from preheater to this blue line is basically this is the supplying of the raw material from the preheater from there itself, right? And cancellation we are feeding over there, and this is conventional process. And this arrow, these blue arrows are in the upward direction. This is in the this is our conventional process. Fine, and we are and over this as I told you, this tower is not a simple way. Actually, this what is called flue gases to the preheater. Okay, this is the flue gases to preheater. This is a complicated arrangement basically, right? So so this is blue is basically this is the material flow, and this is this one is gas flow. The brown dotted this arrow, these are the gas flow in this direction. Okay, so this is a simple process for the mass balance equations. So this is a solar reactor, and CaCO3 is converted into CO plus CO2. Okay, and this solar incident power is reflecting over there in there, and the clean flue gases and the tertiary air we are providing from this and the raw material along with the raw material, clean flue gases, clean flue. This is the heat recovery, basically the waste heat recovery system. From there the flue gases we are getting from there, and the tertiary air, right? And finally we are getting over there the flue gases to preheater and the calcinated material to the clean, right? So the raw material calcination begins only in the calciner. Okay, fine. The tertiary air, the clean are well mixed together with the heat loss to mixing the chamber is negligible. This we have considered for this mass balance. Basically, these are our assumptions, right? So solar reactor must discharge the calcinated raw material and unreacted gas at the same temperature. These are all the basically while we have done this modeling work. These are our assumptions only. Okay, reactor must be attain the steady state condition at equilibrium. Okay, so these are few relations basically. Okay, so solar calcination heat balance equation as is follows. So this is energy flux required, and this QRXL is energy flux required for the raw material calcination, and QHRM this one is energy required to heat raw material from inlet to the reaction temperature, and TA, and this is tertiary the heat contained or the energy contained heat energy contained with the tertiary air input, and this QKG is the clean gas heat input, and this QSR is basically solar calcination thermal energy input. So in this way you can find out very easily this QSR value. QSR is this you can find out this efficiency also. Initially we what we have done, we initially we assume this thermal efficiency, right? So this clean gas and the tertiary gas are supposed to mix perfectly with the exit solar calcination at the same temperature out. This all basically MCP delta T. This is a simple form of the MCP delta T only, right? So this is M, this CP of tertiary air, and this is the temperature difference. This all are those reactions only, all right. And this we have also considered the humidity also over there, and one more factor very important is there. This RD. RD was, I forgot, this one minus RD. This is basically. Okay, क्या था ID? Recovery, basically this is recovery factor only, right? So this is the enthalpy. This all the heat, the energy flux needed in the calcined raw material is provided by this one. This all basically these all the mass balance and the heat balance equations are over there, right? So this all we can use. And solar and thermal needed to run the solar reactor. The calcination raw material is cement producing heat balance equation is like this. Follow the QSR equal to this one. And finally, the mirror surface needed. This whatever this much of heat requirement is there, and that we can calculate with the help of this is the efficiency of the solar corrector, and this is DNI, direct normal radiations. So based on that, number of mirrors we can calculate over there, right? And this optical efficiency is many factors are involved over there. In the cosine factor, this is the reflectivity, right? And this is what is called absorption only, absorptivity only. The required number of finally the number of helistate requirement that we can calculate with the help of the number of mirror divided by the helistate. Okay. So that all we can do. The energy flux reaching on the solar field from the sun, that we can do with the help of this relation, and the process overall efficiency is we can find out with the help of this relation. So I got all the whatever the publication we have, it is with me. I will keep over here. I will leave there itself in this laptop. So if you are interested, then you may go through, right? So these are the different relations, and finally the maximum CO2 reduction. How can we do the maximum CO2 reduction basically, right? So most significant CO2 reduction is possible if all the thermal energy used by the calcination process is replaced by solar energy. So that is theoretically only. So that all we cannot do in practical aspects, right? So this is theoretically. So however, because cement industry operates in 24 hours, right? And if suppose we want to shift all the thermal energy from the solar energy itself, we need huge requirement of the solar thermal energy storage systems, and the cost itself is very high. And at the same time, space is matters. So it is not necessary we do have space in all the cement industry. Fine. So this is theoretically you can consider the maximum CO2 emission that we can reduce. This we can use. This is the conventional, and this is the solar. By implementation of this CO2 reduction, CO2 emission from the reduction from the solar energy implementation only, right? So minimal CO2 emission from the solar cement is determined by the raw material concentration, this, and the quantity of the coal with the rotary kiln, and that we can quantity of the coal and concentration. So that this is the minimum basically. Okay, so minimal CO2 emission that we can this is the feasible basically. This quantity is feasible that we can achieve, right? So in conventional process, the amount of the CO2 emitted is calculated by the raw materials, the CO2 concentration of the and the amount of the coal utilization. So we are considering over there only. Okay, so we as in the beginning itself I told we cannot control this material CO2 concentration, right? That reaction, whatever the CO2 we are releasing with the help of in that reaction, that we do not have any control over there. We can control the amount of coal utilized in the calcination and the this rotary kiln only, right? So therefore, the decrease of the CO2 emission caused by the implementation of solar calcination in the conventional cement plant is computed using this coal with the help of this relation. Again, this is the M mass of the coal used in the calcination process, and the lower heating value of the coal, and this is the specific heat basically of that. Okay, mass. No, sorry. This is CO2 quantity of the CO2. So this software, this NREL software, we have used solar plot, the solar power tower integration layout and optimization tool. It is freely available, that we have used for designing this helipad basically. Can you guess the one side over there, the number of these helipads are increasing over this side? Why this is such kind of, this is very common sense basically. Could you guess why this profile is coming like this? It is not equally spread in all the sides. Why it is in this like this? सोचिएगा, भाई sun move कर रहा है. We are on the northern hemisphere, east to west, and all helipads should face towards southern direction only. So like this. So utilizing NREL's tool, solar plot, the helistatic field configuration is created based on the solar incident power required for solar cement factory to operate continuously, and the solar plot tool for generating the characterizing solar power. So for that definitely 2-3 things are very necessary. How much energy we want, how much thermal energy we want to have, and at the same time the location, the latitude and longitude, and right. So these are the two very essential input over there. So location is basically mainly. So this is a simply solar multiple is nothing. Only if suppose you are designing the system for the 1 megawatt, right, or say the 100 megawatt or 1 megawatt, then you can multiple. You can use the same system for the three times, right? Like 3 times, 4 times, and in that way you can do solar multiple, right? So if there is no thermal energy system, because for the solar energy plant, the helipad must be larger, concentrating of the reactor nominal heat capacity. Because we are directly, whatever the heat is producing from the sun, we are directly supplying to the process of the process to the cement industry. So this ratio is like this. Okay. So this is the energy assessment and the power plant functioning. Definitely, direct normal incident availability is a very essential thing. Okay, in case of the CSP systems for designing solar concentrated power, definitely the good DNI is required. And of course, most of the cement industry are located in either in Rajasthan, Tamil Nadu, Gujarat, like these places only. So we have ample of the solar energy itself, good radiations are over there, good DNI availability is there, and once we have this solar DNI availability, we can design based on the previous whatever the equation we have developed, we have discussed. Based on that, the heliostrate field that we can design, okay, and we can do all the energy analysis, and of course some assumptions and operational constraints are there. That because heat losses, we have heat loss, many heat losses are there, but we have assumed that there is no steady state condition. Like in that way, the many assumptions are there, as we have discussed in the previous slide. And finally, the solar reactor energy input, thermal energy, thermal storage unit, solar full load hours, solarization, CO2 reduction potential, that all these are the output basically. So energy assessment for the hybrid cement production process. This is a small thing only, so nothing like such task we cannot. So this is the whole assessment in the whole energy assessment of cement industry. So in this way you can see. So this is a solar cement plant operating during daytime and the solar multiple. Okay, so just to see over there, the no solar operation below the 20% of the bottom up, right? So that during in 1 year, how much we had the number of hours? 24 hours multiplied by 365, 8760. I think 8760. No, 8670. How much? 24 into 65. कोई नहीं आप देख लीजिए, but we have considered the 800 only, right? Because 8760 हाँ 8760. So we have considered only the 8000 hours only because of this region, right? So these are the different design point of the reactor and process. So and different process are there, the calcination material process over there in this once attaining over there, the excess calcination material thermal energy storage over there, and the maximum operational reactor is over there, right? So this is power versus the time, the solar cement operation during daytime, right? So this again, this is the area, and this is the efficiency, the time, DNI, that all we can calculate the solar power produced, that we can area efficiency, and this based on the heliostrate area, field efficiency, solar DNI, the hourly resolution that we can calculate. So calcination energy output to calculate by the considering the thermal efficiency, okay, that you can calculate the this calcination energy output multiplied by the thermal efficiency, and this heat unit supply by the solar only, right? So in this way, these are the different conditions. When QSR is greater than or equal to the demand, or demand is immediately sent to the sent to the rotary kiln, or otherwise if suppose we have the surplus heat energy, then we can transfer into storage unit. That raw material first after processing we can keep in the storage unit until has achieved the design load. Fine. So so with this way we can calculate the different these these values. Okay. So and you know, so no further raw material is generated in the calcination thermal energy storage. This is another conditions. So difference between the solar calcination output and input of the cleaner filled by the solar thermal so far is not empty. This the conventional energy fire, the calcination start operating when there is no calcination material, the thermal energy loss requirement is more, and so these are the different conditions of the plant that we have studied. And you can calculate finally that total time operating using fossil fuel, the total time operating using solar, and calcination process for the this solarization, and annual fuel saving. Finally, so annual fuel saving you can calculate with the help of these relations. So this all you can write equation EES, or a simple Excel sheet you can make, or otherwise MATLAB itself. So only the multiplications are there, nothing, some conditions over there, no, but very simple, right? So, so based on this model, the storage hours, thermal energy output, the solar reactor, that all we can do over there. The solar thermal size is assessed the optimization techniques, okay, So conventional firing, full load, these are the different, so means ultimately you can, the complete solar thermal system is including storage or without, with storage and without storage, that you can optimize basically. Different parameters you can optimize very easily, right? So this is case study 1 where the Kotputli cement plant, we have considered it is situated in the Jaipur Ultratech Cement Limited manufacturing unit, and production capacity 4 million tons per annum, and the actual production is for the 2020 that 2.37 million tons per annum. Okay, this all data has been taken from Indian Minerals book 2020. So as we know, by designing the solar thermal system or solar energy system, solar energy conversion system, we definitely need this radiations and temperature. However, this temperature, deeper temperature is not required at all. But because we wrote, because of this software has given this value, though it is not required. Of course, the relativity we have considered over there. Okay, pressure. Then this FF, please don't misunderstand with the fill factor. It is not the fill factor over there. This is wind velocity. Fine. So because Solmat software, it is coming like the FF. Okay, this is wind velocity basically. So that these all factors are needed to design the solar thermal system, and based on the location, you can put over the Solmat over there. The monthly global horizontal irradiation and the direct horizontal irradiations at the plant location you can find out very easily. So diffuse and global, again the monthly minimum and maximum temperature at the plant location, right? This is for Kotputli plant only. The monthly sunshine duration for the plant location, all right, sunshine, and then and this. These cases we have considered the 100% replacement, that is not possible. This is the theoretical only. 90%, 80%, 70%, and in my point of view, the 70, 60, and 50% replacement is possible. Fine. So and the thermal losses we have considered 40%, 30%, and 15%. Of course, the thermal losses also we cannot avoid, even though we are insulating everything very nicely, that we cannot avoid, right? And at least the 15%, up to 15% we can control, right? So specific heat is a 3182 kilojoules per kg of the CEO, and this amount of the limestone in the raw material 94%. Ultratech this Kotputli plant, CO concentration of lime this is 42%. 42%. The working day annually 65. Actually, the system is working. We have considered the means. This plant was working all the 365 days, right? So the clinker production rates, these all from here to here. These data we have taken from the actual data. These are the actual data. Only we are considering for the present study these things, right? These all data we have taken from the their plant itself. So clinker production rate is 6,500 tons per day. So this is a huge capacity. Okay, the plant location DNI is a 438, right? So now, oh my God, this is again very blur. So anyway, this 100%, 90%, 80%, 70%, 60%. This is basically the replacement, right? So how much is thermal energy we can replace over there? And these are the 15, 30, and 45%. These are the losses. And for different cases, these losses are, we have considered the solar power out from the solar reactor depending on the power losses, and the mirror surface depending on the thermal losses, number of the helistrait, load surface depending on the thermal losses, and the solar incident power for the helistrait in terms of the megawatts, and the net conversion solar chemical efficiency. So I will keep over there this PDF file. So you may read very clearly. I think this is not visible properly. So this all the factors are given over here. This we can calculate with the help of all those relations that we have discussed in the previous slide. Solar power, mirror surface, number of helistrait, load surface requirement when the concentrated solar is implemented in the conventional plant, right? This Kotputli. Just we see over there. This is solar calcination and the conventional cases, right? So only difference is not much. and the difference is only the 400 in thousands of the tons of the CO2 emission by implementation of this solar calcination. 400. Yes, 15. This solar calcination is 1576 and 1995. This is 19. So around the 400 and thousands, right? So this, just look at over there. Our purpose was to estimate this how much potential we have to replace this to minimize or the reduction potential of the CO2 emission. So potential of the solar calcination technology to reduce the CO2 emission in this plant. So still it is good figure, right? Because we have some constraint, like we can only replace the whatever the fuel requirement is there. The coal we can replace. Otherwise, whatever the CO2 emission in the reaction, it's a limestone reaction that we cannot. That will happen ultimately, right? And now the economic analysis we have considered for the different losses. This is for the thermal losses over there. This is the 15, 15, 13 and 45. Okay, just look at over the PVT analysis. This is 6.2, 7.8 here and 10.4. Of course, whichever the thermal losses is, definitely we will have the PVT payback peak time is lesser. That all depends. And this is reverse through this IRR analysis. Of course, this higher IRR is means always the preferable. So 10.2 for this 15% and 30% losses of 8.3 and for 45 this is 5. So this is PVT analysis was 6,500 tons per day. Solar cement plant based on the thermal. This is IR analysis for the same plant, right? And this is another case study. This is just a study based on the whatever the data we have. Okay. India is dominant in the cement production sector. 7% of the installed capacity worldwide. Okay. Installed capacity was 500 million tons in 2021, while actual production was 294 metric tons. In the period of 2021 to domestic production grew this much of government plan to smart city and expansion. This all basically those are data only. Now this is basically the production of state-wise in India, the 2021. For the year of 2021, the state-wise, and over there, the two states, one is the Rajasthan, another one is Andhra Pradesh, and this Gujarat also, and this Telangana, right? These are the state where the production is highest, right? And of course, you will find this DNI also you will find means better or comparatively good in other states like the Odisha and others, in these states itself, right? So these are the different cement plant like Portland plant, Pozzolan, and of course these are basically the main industrial type. This is the integrated cement plant. Cement grinding, only grinding is there. The cement clinker plant, only clinkerization is there. After clinkerization, two processes are there that is not conducting over there. So and the secondary industrial on cement terminal. This is the filling these bags, the preparation of bags and packaging plant, drying water, fiber and pozzolan quarry. Means so these are basically the main plants, and in fact the main plant is only the integrated cement plant. In this cement plant we have all the processes from raw material to final the bag. We will get at the end the cement bag, right? So in this plant, so these are okay. This figure, this map is integrated and clinker plant across India. That we can see. This is basically just a study actually based on the latest based on study literature we have. So list of the nation's cement industry, the annual cement production of each plant in the country. I'm not able to see this. What is that? Whether the plant produce cement clinker. Okay. Okay. Fine. Yes or no. Otherwise, is suitable for the solar integrated process heat. Right? So if it is suitable, then it is fine. I estimate the total thermal energy requirement calculation process and that all this flow chart basically. Similarly, this is the methodology what we have discussed. The method for determining CO2 mitigation potential through solar integrated process heat in the Indian cement industry. These are the location wise data for the cement plant in the Rajasthan. And DNI of the plant across India. You can see number of the cement plant which are located on this DNI. Of course, the 23 where the DNI is having the 1300 to the 1400, 1400 to 1500, 18, and this 1500 to 1624. So means we have the huge potential for implementing the solar energy. At least these plants. Okay, even this one, this also. Of course, this is more than 1000, so this is also feasible. Yeah, more than 1000 and watt per meter square or watt hour per meter square. This is so these all are feasible basically. Right. So DNI plant this fine. So in this way, this cement plant, cement production and thermal energy is requirement for the preferred location with the cluster of plants in India, that you have all the data over there, right? So this annual amount of the CO2 mitigation with the different plant, JK Cement, Karnataka, Rajasthan, and all the potential of solar energy process heat system to reduce the CO2 emissions to prefer plant, which is DNI is more than 1700 kilowatt hour per meter square per year. Right, these are the preferable locations where we have good opportunity to reduce the CO2 in these. So annual amount of the CO2 mitigation in state wise, of course, Rajasthan, Andhra Pradesh, again Gujarat, Telangana, because of the availability of the solar energy, the state wise CO2 emission in the cement plant implementation. That all exercise we have done in the same software itself. Means 2-3 software integrated basically for this work. 3 software. So these are the technical challenges, and further we can study, and the preheater tower load capacity itself that we can work out. The transportation of the raw and the calcinated material, over the complete energy analysis we can do in this sector. The scaling of the solar reactor, okay. And storing the calcinated material, if we suppose have the excess amount of solar thermal energy that we can calcinate material, we can do it and store for the later use. That we can consider in calculation. So, and finally, the utilization of the central tower system with the solar reactor at the top of the tower is best way to integrate the CST. Okay, it's fine because losses are less in this case. The suggested design model does not need any major change in the conventional plant, or only you need to integrate the solar thermal system, CST system, so that's all. So economic analysis, design model PVD increases the thermal losses, is also not attractive for the 45% thermal losses. There are a lot of barriers that exist with the implementation of CST technology, scaling up solar reactor, transportation of the raw and calcinated material, storing material are major barrier. Conventional cement plant that is situated location in the DNI more than 438, तो वो ये हमारे पास खूब opportunity है ये watt per meter square. Can we use this solar design model, and conventional plant that have allocated load storing the large number of energy state. Implementation of the CST, this concentrated solar energy cement plant, mitigate large quantity of this. So this is all about from my side, and now you can guess whose work I was discussing. He is your colleague. He has done very excellent work, and in fact all credit goes to him. I was just presenting his work, right? He is Mr. Niranjan Sahu. He published very good number of the research paper, Journal of Cleaner Production with the impact factor 11, and then